The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Today we're talking about beating impossible odds, both in fiction, stranded alone on the planet Mars, and with rocket engines that seem to defy the laws of physics. Hello and welcome to Science for the People. I'm Rochelle Saunders. A little later on, I'll speak with Ethan Siegel about the impossible space engine recently tested by NASA that seems to violate the law of conservation of momentum. But first, I'm joined by Andy Weir. Andy was first hired as a programmer for a national laboratory at age 15 and has been working as a software engineer ever since. He is a lifelong space nerd and a devoted hobbyist of subjects like relativistic physics, orbital mechanics, and the history of manned spaceflight. He is also the author of the novel The Martian, which was originally self-published and through word of mouth from nerds like you and me became a bestseller. Andy, welcome to the show.
Hi, thanks for having me.
Okay, and people, there will be spoilers. Lots of them. You have been warned. Okay, so for those who haven't read the book but are still listening because they don't care about spoilers, can you give us a quick summary?
Sure. The story is about an astronaut named Mark Watney, who is on the third manned mission to Mars. And he gets injured during an emergency evacuation, and his crew believes that he's dead, and they have to leave without him. But it turns out he isn't dead, and now he's stranded on Mars. His communications equipment is broken, so he has no way to tell anybody that he's still alive, and he needs to try to survive with just the equipment that he has on hand, which was intended for a short-term mission.
So, based on what I've read, both in your book and a little bit afterwards, doing some research, you, sir, did a lot of research for this book, and apparently the science in it is pretty much as accurate as you can make it. Is that true?
Well, yeah, I tried my best to make the science as accurate as possible. As you mentioned in your introduction, I'm a nerd, and so when I'm reading books or sci-fi, it would always bother me when I'd run into something that just made me cringe because of how inaccurate it is. And it's kind of funny, like, I don't mind a warp drive in a story, I just accept that. But when somebody's walking around on the moon without a spacesuit, that drives me crazy. So if you break the rules a lot, that's fine. But if you break the rules a little, it drives me crazy and takes me out of the story. So I wanted to make sure that my story was as accurate to real science as possible.
So you call yourself a devoted hobbyist of subjects like relativistic physics, orbital mechanics, and the history of manned spaceflight. And I don't know that most people would think of those things as hobbies.
Well, anything's a hobby if you like doing it and you do it for free. I don't know. I just these are things that are really interesting to me. In The Martian, for instance, they go from Earth to Mars and back to Earth, and I calculated all the orbital trajectories and everything that they'd need to take for their ship, which is a constantly accelerating craft, and it was really complicated, and I had to write software to do it. But I really had fun doing that. I like that kind of problem solving.
I read a lot of pop science books, including a lot of space and physics books. But you sound like perhaps you might read something a little heavier?
Well, mostly what I like to do is just search around online and find articles about what I'm interested in. Like, for instance, the supposedly reactionless engine you're going to be talking about later in your show. I eagerly read everything about that as soon as I heard about it. That sort of stuff is really interesting to me. Also, yeah, I like reading nonfiction about the space program. If anybody who likes that, I'd highly recommend Packing for Mars by Mary Roach. Yeah,
I can also vouch for that one. I want to talk more about the book, and seriously, for science nerds, this is the best sort of fiction, because no one puts that much math and engineering in a book, but doesn't do the research to make it accurate, and it really gave me nerd goosebumps, so thank you. But I'm curious, because I'm sure that there's something in the book that's not 100% accurate, so what parts of it aren't as accurate as you'd like them to be?
Well, there's a few places. The biggest inaccuracy is the sandstorm at the beginning. Right at the beginning, there's a sandstorm. It's threatening to destroy their ascent vehicle, so they have to leave. It's what injures Mark. That's kind of the main event that starts the plot. Thing is, the sandstorm on Mars, it's true that Mars has 150 kilometer an hour winds, but Mars's atmosphere is very, very thin. It's less than 1% the density of Earth's atmosphere. So the inertia of the wind, the actual momentum of it hitting you, is very, very low. And it would feel a 150 kilometer an hour wind on Mars would feel like about a 1 or 2 kilometer an hour wind on Earth. It would be completely harmless. But a lot of people don't know that. Most people think that a sandstorm on Mars would be like a sandstorm on Earth, just really devastating. And so I had to make a decision. I decided to go ahead and be inaccurate. I mean, so I knew that was BS when I wrote it, but I stuck with it anyway because it's a man versus nature story, so I kind of wanted nature to be the initial problem. 99.9% of people don't know that the sandstorm wouldn't really work out that way. And so I said, like, well, some people will be disappointed by that, but hopefully I'll buy back their affection with the rest of the book's accuracy.
And you did very much so.
Hope so.
How long did it take you to research some of this stuff? I'm thinking the botany theory around growing potatoes on Mars, because this was one of my favorite bits.
The botany of the potatoes was actually not too bad. That was just quick research online. Well, not quick. I mean, it took a while, but all told, yeah, people often ask me how much time I spent researching, and it's hard to answer because I would research and write. It's not like I did all the research first, then all the writing second. But it did take me about 3 years to write the book, and I'd estimate I spent about half the time researching. So I'd say maybe 18 months of research total.
What would you say was the most intensive research you did for this book, the bit that took the longest?
Probably the orbital dynamics. So Hermes, which is the ship that takes them back and forth between Earth and Mars, is not a point acceleration craft. In other words, it doesn't just like burn a rocket engine and then coast until it gets to its destination and then burn an engine again to, fall into Mars's orbit. What it does is it's constantly accelerating with an ion engine. An ion engine produces a tiny bit of thrust, but constantly over time. And the benefit is it takes much less reactant mass. You're just throwing argon out the back of the ship. The fuel that you use doesn't need to be anywhere near as heavy as traditional rocket fuel. So that ship is constantly accelerating at 2 millimeters per second, which is a teeny, amount of acceleration. But if you do that for months, you get a pretty good head of steam. And calculating that was extremely complicated, like figuring out how to do an intercept from Earth to Mars using just that tiny acceleration and constantly on. I couldn't figure out how to do the math for it directly, so I wrote software to simulate it, and I made actually an app that lets me kind of change the ship's heading and stuff like that here and there and just kind of work out a trajectory that would do it. And that was really fun, too, because I'm a computer programmer, so when I'm presented with a problem, I want to write a computer program to solve it, right? When the only tool you have is a hammer, everything looks like a nail.
I also heard that, in part because you wrote this software to help you understand the orbital dynamics and how the intercept course would look for some of the scenes in the book, that you actually have a specific time frame that this story happens in.
Yeah, because I was doing the orbital intercept, the orbital trajectories and calculations, I had to pick a launch window. And so Earth and Mars move around the sun at different rates. So their relative position to each other changes all the time. So I had to pick a launch window. I had to say, like, okay, Earth and Mars have to be at these points in their orbit. So when is that? And so it was interesting because I knew the exact date of every moment in the book because I knew when their launch window was. I knew how long it took them to get to Mars. And, of course, most of the book is delineated into log entries that tell you exactly what day of the mission they're on. So it's like, log entry Sol 114 or whatever for the people who haven't read the book yet. A Sol is a Martian day, the amount of time it takes Mars to have a day, which is about a little over 24 hours. It's 24 hours and 40 minutes. So I didn't want to tell people the exact dates because I didn't want them focusing on, the future or anything. I wanted it to kind of take place now-ish or slight future. And I just didn't want people focusing on exact details of dates. But one of my alert readers was able to back calculate the exact date that everything takes place on based on information in the novel. And I thought that was really cool. He worked it out from the communication delays between Earth and Mars and from knowing that Thanksgiving was on a specific date that was mentioned and a few other things. And I thought that was really cool.
That sounds like you made one space nerd really, really happy. So you mentioned having to calculate all these intercept trajectories and velocities, and another spoiler alert for people who have just tuned in. But at the end, there is a very complex series of interceptions and things that have to happen, and I was riveted on my seat. Can you talk us through how that works and how plausible that actually is?
So at the end, the Hermes is coming back for Mark, and Mark is ascending off of Mars with a different Mars mission's ascent vehicle. The math on that actually wasn't that complicated because for that I didn't have to actually work out the details of like, okay, here's the ascent, here's this, that, and the other thing. All I had to do was say like, they had a plan that would have worked, but it missed by this much, and everything else is just like, okay, How do they close this gap of several kilometers when they're out in space?
You're listening to Science for the People, and today we're talking with Andy Weir about his best-selling novel, The Martian, about a man trying to survive alone on Mars. And if you're just tuning in and this book is on your to-read list, be warned, there are spoilers. So most of what you've written is possible, but if I were to pin you down, how plausible do you think it is for someone to survive alone on Mars in the setup you described?
Pretty low chance of success. You could say that Mark got very unlucky to be in this scenario in the first place, but also he got very lucky in a lot of ways throughout the book. I tried to keep them as minimal as possible, but, the initial scenario where he gets a spacesuit punctured and then doesn't die immediately is pretty lucky. And then there are all sorts of things that could have gone wrong during the course of the story that didn't. Certain pieces of equipment that if they'd broken down, he would have died just immediately. And so they just didn't go wrong, right?
Right.
And so he got pretty lucky.
It's really interesting. You don't shy away from the math in your book. And I know some people who hate math who also love the book. Something about a man's life being dependent on this math and engineering maybe makes people take it more seriously rather than just skip over it. What do you think?
Well, that was the biggest challenge for me while writing the book. I needed the reader to understand the basics of the math behind what was going on, but I also didn't want it to read like a Wikipedia article, right? I wanted it to be interesting. So I had to really be careful drawing that balance between saying, okay, here's the information I need them to have. And I did a whole bunch of extra work that I'd love to brag about, but if it's not immediately and critically important, don't put it in there. First off, I wrote the book for nerds, right? I wrote the book and I was posting it to my website. And so my target audience were people like me who I figured would all be really interested in the math. So that was part of it. It ended up working out well, though, because the people who aren't interested in the math or aren't interested in the science, they just tended to skim over those sections. And it wasn't even that big a deal to them. They'd just go like, oh, okay, they're talking about math. They didn't put any effort into absorbing it or understanding it. They just accepted it as true and moved on. And so I think that worked out really well. People would kind of selectively give as much attention to the math. They'd give it as much attention as they cared to and ignore it if they didn't like it.
I talked to a couple of people, both math-inclined and non-math-inclined, who had read the book and really enjoyed it. And I found that most people actually read through the math. And I think part of that is as you're reading through the math process or the engineering process that Watney goes through to try and solve some of his varying and diverse crises, the math actually tells a story. It's riveting to some extent because you understand how difficult the problems are. You sort of sort or walk through the difficulty levels with Mark as he's trying to figure out the problems. So I think most people probably have read a lot of the math and engineering, and I think it actually made the story better.
Yeah, I hope so. That was the goal. Also, one thing that helped a lot was just making a first-person narration with a smart-ass narrator. So there were a lot of jokes in there that hopefully pulled the reader through.
He is a very interesting, sort of smart, let's call it smart-ass character. And that's definitely, you really cheer for him, especially at the end. You really want him to make it.
Yeah, that was what I was hoping. I mean, if he was just this stoic astronaut type, the novel would have been very dull. So I needed him to be really, really interesting and compelling.
Going back for a second to the math and the engineering that's actually in the book, do you think that you were able to keep that in part because A, it was self-published, B, you knew your target audience were hardcore science nerds, and perhaps if you had a publishing house or an editor that you were working with, that a lot of that would have had to have been cut?
Well, not if it was the editor I ended up with. Once Random House said, like, hey, we want to make a print edition, and I had an editor. That editor loved the science aspects of it, and he actually had me expand some of them. He'd say, like, oh, this part it wasn't really explained well enough. I didn't really get it. I didn't understand it, and I don't think other people would. So can you expand on it and explain it in more detail? So I think the editor I ended up with, whose name is Julian Pavia, and he works at Crown, was very much in favor of the science segments.
Do you think publishers or people in charge of picking what movie or TV show or book is coming out next might underestimate people's ability to absorb this kind of technical information?
I don't know. And there's a big difference between books and TV and movie, right? Books tend to be much more toward target audiences. Like science dorks will read The Martian. It has some broad appeal, but for the most part, it's people who like science and science fiction. But when you're making something TV or movies, it costs so much to do that. If you want to turn a profit, you need to appeal to a much broader base. You need to it doesn't work if you want to make high-budget TV or movie for a niche audience. You just won't make your money back. You'll go out of business. Books can get away with that, no problem. But TV and movies, they need to be something that everybody will like.
You are tuned in to Science for the People, and we're speaking with the author of the novel The Martian, Andy Weir. And if you've just tuned in, you should note there may be plot spoilers ahead. So I've heard you based a lot of your mission design in your book on the Mars Direct project. For those listeners who've never heard of it, can you give us the cliff notes of this project and why you chose it as a base?
So Mars Direct was invented by, a number of people, most notably Robert Zubrin. And it's a mission plan for how to do a manned Mars mission. The critical part of it is that you send the return ship and all supplies to Mars first before you ever send people. And then the return ship can sit on Mars and use a process that actually turns the Martian atmosphere into rocket fuel, which you can do. You take the Martian atmosphere and you need hydrogen, and then you need a bunch of energy, which you'd get either through solar cells or whatever. And you can make high energy rocket fuel out of that. For every kilogram of hydrogen you bring to Mars, you can make 13 kilograms of rocket fuel. So this way you don't have to carry all that mass, your return fuel, you don't need to carry it all the way to Mars. And that's critical because every kilogram you want to send to Mars takes like tens, maybe even hundreds of kilograms of fuel. And so the main plot, the main trick of Zubrin's Mars Direct is that they call it ISRU, in situ resource utilization. I think everybody agrees that something like that would have to be done if we were going to have a manned Mars mission. However, this was, I think Mars Direct was invented in the 70s or 80s. So they didn't yet know about new technologies that exist in the more modern era. And among them is ion engines. And I really think ion engines are going to be one of the main factors in manned interplanetary flight. So my version is, I said, okay, first off, the way you get back and forth is with a big ion engine craft. Second off, in Mars Direct, the plan was to have the entire return ship on Mars, which then would lift off of Mars and then go back to Earth, right? But I don't buy that because it means you would need to have the entire ship that they're going to live on the whole way back from Earth be on Mars and spend all the fuel to get back up. So what I did was I said, no, they just have one ship, a big ship. It never lands. And then they use a little ship to get to the surface, and then they use the MAV on the surface, which also uses that same reaction to make fuel, just to get back up to their main ship, and then their main ship uses its ion engines to go back to Earth, which I think would be a tremendous cost savings.
The character of Mark Watney is really great on multiple levels. We mentioned his sass, let's call it.
Sassy.
But I think he just is a great character as a scientist. He doesn't just come up with an idea and plunge sort of recklessly ahead. He does the math, he tests things, he does a series of proofs of concepts with increasingly more difficult tests. He's extremely methodical.
Yep, his life depends on it. I could get away with a lot with Mark because I knew that he's not just some normal guy. He's not like he was minding his own business and got sucked up and sent to Mars. He's an astronaut, right? I mean, he must have beaten out a bunch of other candidates for that spot. He must be extremely qualified and extremely well trained. So I never needed to explain why he was so good at the stuff that he's doing, which is just a huge relief as a writer. You don't need to delve off into some Slumdog Millionaire thing on the side explaining why he knows these things, right? You just get to write it. And that was a huge benefit. So I could kick back. I could spend a month doing research and figuring stuff out. And then Mark just knows all that stuff in advance and quickly works it out in an afternoon.
So one of the things you didn't really get into, but would be a huge problem to deal with if you were actually stuck on Mars alone, is the psychological toll. Why did you decide against tackling that in this book?
Right. That was another deliberate decision on my part. And the main reason is I just didn't want it to be that kind of book. It could have very easily, I mean, realistically, if somebody was stranded alone, if somebody was in that situation, and he was there for a long time, he was there for 500 and some odd days. So that's almost 2 years, a year and a half at least. It would have a huge psychological toll. That's just the solitude alone would be devastating to any human. And then the constant stress and threat of death and just the extremely unforgiving and harsh environment. and for large portions of it, no contact with other humans of any kind. It could have been a dark, depressing story about a man's struggle against like crippling loneliness and despair. But I didn't want it to be that kind of story. I wanted it to be about problem solving, about cool technical MacGyver-y solutions. And so I decided to just kind of work around it by saying, well, Mark is, once again, that same excuse. Mark is made of sterner stuff. He was selected in large part for his ability to deal with long periods of solitude and for his optimistic and attitude and strong like internal character. So that's my excuse for why that didn't happen. But the real reason is I just didn't want it to be that kind of book. I didn't want it to be deep and introspective. I wanted it to be all about the science.
One of the projects I'm watching is the high seas Mars simulation missions taking place in Hawaii, which are specifically studying psychological and social effects of putting 4 or 5 people in a small enclosed space together for a really long time. Do you think these kinds of simulations are important for eventual long-term successful missions?
Oh, absolutely. They're critical. One of the biggest issues facing long-term spaceflight like that is how do people get along for that long? I mean, right now we have people who are assigned to the International Space Station, and that's a crew of 6, 3 to 6 people, depending on when. And they'll be up there for 6 months at a time, right? So that's fairly claustrophobic, and you're with the same people, and so we're learning a bit about how that works out. But if you were going to do a manned Mars mission, you're going to have, 6 people or so in close proximity to each other for literally years and with no possible escape from each other. Like if they start developing social or interaction problems between them, there's going to be serious problems. There's no way out. So they need to learn all they can about, well, basically cabin fever and find out what the psychology is behind it, how to stem it off, and and the most important thing is how to select people in the first place that won't have that problem or will keep it under control.
This is Science for the People. I'm here with Andy Weir, author of the best-selling novel The Martian, discussing his book and the science of being stranded on Mars. And of course, this is also your spoiler warning for those of you who have just tuned in. So you don't just stick Mark Watney on Mars. You also pick up the story on Earth, where NASA is working just as hard to get him home as Mark is working to survive. Why did you decide to cover this side of the story as well?
What's funny is originally when I was writing it, I didn't plan to do anything other than Mark's point of view. However, it just became more and more clear to me that the stuff going on at NASA would be interesting, and leaving it out would be denying the reader a bunch of, interesting plot and storyline. The short answer is I knew it couldn't possibly take that long for NASA to realize that he was still alive. And then, everything that happens from that point on becomes, like, well, crap, what do we do now? And so, I don't know. I was really happy with the way that it turned out, because then it has this other aspect to the story of the whole world rooting for him and kind of a Truman Show thing going on where everybody's watching his movements and hoping that he does all right. And I was really happy with how that turned out, which is funny because at the time when I was writing that first NASA chapter, I'm like, this might be a mistake. I might just be like deviating from a first person narrator that everybody likes to wander off into a whole host of other characters that are only being introduced here in chapter 7.
What's really interesting about the NASA side of the story, I think, is that there's a part of the reader that wonders when someone will step in and say, it's too much money, we can't do it, shut it down. Which makes that side of the story more intense, and even though there's not a lot of traditional action there.
Yeah, and there's just a constant problem of how to deal with this. That's another thing people call me out on, is people say, like, would they really spend that much money and put that much effort into saving one man's life? And, I can't answer that, but I can say it comes up a couple of times in the book where somebody I think asks in a press conference, it's like, well, you've spent hundreds of millions on this, like, how much is too much? And the answer that they give is, well, we spent hundreds of billions to send people to Mars just to have a 31-day mission. Now we're getting, 20 times that much time spent on Mars. Now we're getting free extra bonus Mars research time for basically a bargain if you do the math. So that's kind of their explanation for why they're doing it. But really, the reason is far less cynical. It's just they want to save him. It's an emotional reaction.
So there are a couple of real-world plans to get people to Mars. Some private initiatives, some publicly funded ones. Any thoughts on those?
Well, I believe the first manned mission to Mars will have to be like a government thing. And it would probably be, despite how it's portrayed in The Martian, I think realistically, first manned Mars mission would probably be a large international effort, kind of like the International Space Station. I just don't see any other way for it to work because it would cost just so much. And it's the sort of thing that like countries, it would cost the space budgets of multiple countries combined to be able to make that happen. So that's like number one. I think it would be international. Now, yes, there are private industry ideas like Mars One, and I know Mars One gets a lot of airtime, but I don't take them seriously at all. I think they're a good think tank for coming up with issues that need to be solved and plans and ideas, but I don't think I think their claims that they will have people on Mars, that they'll be able to actually put people on Mars are ridiculous. And their funding streams are they plan to fund it with reality TV. Well, I can tell you no reality TV show makes enough money to fund a Mars mission. Like, if you took all the proceeds of American Idol and put them toward a space mission, I don't think you'd even be able to send a probe. Well, maybe India would. They did a really cheap probe. It was awesome, like $70 million.
There definitely does seem to be a push, or at least a perception of a push, to put a person on Mars. Do you think that's a good thing?
Yeah, I think it is. I think manned spaceflight is important for the one simple reason that it is a step toward colonizing other worlds, and I think that's important to our species. I feel uneasy having our entire race be on a single planet. Like, we're one good, strong asteroid impact away from extinction. But if we were in two places, even if we were just on the moon as well, then we're safe. So if you think of us as some sort of planetary mold, we need to go. We need to infect another planet.
I like that. I will now think of the human race as planetary mold for the rest of my life.
Well, that's what we do. We're just kind of on the surface, kind of spreading out. Grow a lot, spread out. Yeah.
There does seem to be a huge interest in the robotic missions off the planet. The Curiosity rover on Twitter has 1.8 million followers. The Philae lander has 375,000 followers, and Rosetta has almost 300,000 followers. It seems like there's definitely a renewed public interest in space missions. Absolutely,
and I think that's great. People are interested in this stuff. They want to see what's going on, and also I think people take pride in the technical accomplishment of it. The Philae lander, especially. I mean, not to take away from Curiosity, landing something on Mars is very, very hard. The Philae lander was, and Rosetta in general, that was just a glorious orbital path that took it through lots of exciting twists and turns. I mean, it went to. I forget all the sequences it did just to get out to that comet, and then to actually put a lander on it was just amazing. And then, of course, Curiosity. I mean, people are very fascinated by Mars. Mars is just an interesting planet, and we learn so much more about it. Curiosity has already discovered two things that screw with The Martian, my book.
How convenient of it.
Yes, it landed after the book was written, and like one thing it found out was, first off, there's a huge amount of water locked up in the soil of Mars. Something like for every cubic meter of Martian soil, there's about 35 liters of water, which is like plenty. So Mark, all this stuff Mark had to do to get water, probably he could have just baked it out of the soil. But I could get away with it still. I could say like, well, he's in Acidalia Planitia, which is a desert, and the Curiosity rover, that's over by Mount Sharp, which is like thousands of kilometers away. Totally different area, I can claim, until somebody proves me otherwise. And the other thing they found out was that there's a lot of that the soil in Mars is like riddled with phosphines, which would make it impossible to grow anything in. But then, if I'd known that, then I would have said, okay, what do you do to make it suitable? And then I would have had Mark do that.
So more research would have solved that problem.
More research, yeah.
Do you think the advent of social media and the fact that hundreds of thousands or millions of people can follow some of these missions in real time has increased the engagement level?
Probably. I would say it's not just social media. I would say just the internet in general. The ability to get the information when you want it is critical for these sorts of things, because the information comes in slowly and methodically. It's not like there's some... I mean, you watch the landing, and that's exciting, right? You can watch that live on TV. But beyond that, it's the sort of thing you check up on once a month or so. And so having random access to the data is I think, what people like. They go like, oh, I wonder what Curiosity's up to.
So as a space nerd who writes books that shows the work, do you have any recommendations of other sci-fi books that would appeal to people who loved your book and want more?
Well, for starters, whenever asked about sci-fi recommendations, I always have to recommend Ready Player One by Ernest Cline. It's the best book I've read in maybe 10 years or more. It's not a hard sci-fi book like The Martian, but it is science fiction, and it's very, very good. If you want hard sci-fi, the stuff that has like technical accuracy, I'd recommend pretty much any of Larry Niven's stuff, like Ringworld. And now it's all very kind of high concept. Like here's an artificial series of planets in orbit around each other, et cetera, et cetera. But he uses real science. But my favorite authors, the ones that inspired me, the ones I grew up reading, were Heinlein, Asimov, and Clarke. So if I had to pick one book out of all of everything for sci-fi enthusiasts to read, or people getting into sci-fi, I'd say I, Robot by Isaac Asimov.
Andy, thank you so much for being here. The book is both fascinating and a really great read.
Thanks for having me.
If you want to learn more about Andy Weir or his novel, The Martian, you can check out andyweirdauthor.com, a link which you'll find in the show notes for this episode on our website at scienceforthepeople.ca. We'll be right back to talk about impossible space drives with theoretical astrophysicist Ethan Siegel after this. Stay tuned.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
I'm here with Ethan Siegel, theoretical astrophysicist and professor at the Lewis and Clark College in Portland, Oregon. He has previously taught at the University of Portland, the University of Wisconsin, and done astrophysics research at the University of Arizona. He writes the blog Starts With a Bang on the Medium Network, and his first book, Beyond the Galaxy, How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe, is due out later this year. He also occasionally pops onto our show to lend us his cosmological and astrophysical expertise. Ethan, welcome back. Always good to have you.
Thank you. It's my pleasure to be back.
Okay, so I've been seeing this story pop up periodically for ages. Can you tell us about the M drive?
So the M drive is often called NASA's impossible drive that could take us to Mars and beyond. And the idea behind it is, of course, wow, wouldn't it be fantastic if we had a way to generate energy, to generate thrust, to generate propulsion that didn't require any fuel sources on board, that we can just use the energy that's out there in the universe, from the sun, from stars, to propel us. Right, this is a huge problem if you want to take a long journey, if you want to take a long distant journey, you either burn up all of your fuel at once, which is very difficult, right? Because if you want to move a large mass, you need to bring a large amount of fuel on board to propel you. But the more fuel you bring on board, fuel is massive too. So you need even more fuel if you want to accelerate that. So you run into this problem very quickly that the amount of energy and the amount of fuel required to launch a massive heavy object up to a high speed, it becomes prohibitive. So we're looking for ways, how do we get there faster? How do we make it happen using less fuel? If we can find a way to use just the sources of energy that are out there in the universe to propel us, that's going to be a huge saver. So the idea of the M drive is we can use EM is for electromagnetic. The idea of it is we can just use energy that's out there in space and pump it through this cavity, this M drive cavity, and something will happen inside related to electromagnetism where we will get this thrust out at the end. That it doesn't cost us anything. We just sort of take in energy, maybe from solar panels or something like that, and convert it into thrust. Wouldn't that be great?
It does sound really like a nice way to travel through space. But the fact that it's got the moniker impossible makes me a little bit skeptical.
And it should, right? When you say impossible, you think, well, what does impossible mean to a scientist? Right? We have our laws of nature. We have the laws of physics as best as we understand them. And we think we understand them pretty well, particularly how that relates to normal matter, stuff like you and me, stuff made out of atomic nuclei, protons and neutrons, and electrons. So things made out of atoms, molecules, solid matter. We think we understand that pretty well. You know, we've got the standard model of elementary particles. We've got the three forces that they interact with. We've got gravitation, we've got electromagnetism, the electroweak force, and we've got the strong nuclear force. So between that, the nuclear forces, the gravitational force, and the electromagnetic force, and how those forces interact with matter, we think we understand that really well. And so when they say NASA's impossible drive, when they say the M drive or the Kinney drive, as it's sometimes called, what they're talking about is, well, the standard theories that we have, the theories of how particles work, how forces work, this shouldn't be happening. But, you know, one of the beautiful things about science is it's an experimental thing. So if you can devise an experiment that gives you a result that isn't what your theory predicts, that either means there's something flawed about the experiment you ran, or it means, maybe our theory is incomplete. Maybe our theory doesn't apply to everything. And that's the exciting possibility. That's the exciting possibility of what this could be. If you can build a device that does something that the laws of physics don't jive with, that aren't predicted by the laws of physics, but you can repeat it and you can do it independently and you can get solid, robust results out, you may have just discovered a new law of physics. You may have just discovered a new property of this universe. And if we do that, that can have tremendous implications for not only what we think the fundamental underlying rules that govern existence are, but also for applications of what we can do as far as technology goes. And in this case, if the M drive is real, it can be enough to maybe take us to the other planets and beyond, to take us to the stars for the first time.
So let's talk about the M drive specifically. Now, is there any public information out there, or do we know how it's supposed to work?
You know, the thing is, when you're an inventor, it's kind of your prerogative to publish as little or as much as you want. And one of the, for better or worse, ways we run things in this country is the U.S. Patent Office doesn't issue patents to devices that purport to violate the laws of physics, right? We've had instances all the time where people are like, I've invented a perpetual motion machine. And the patent office says, no, you didn't. You're not getting a patent for this. And someone says, oh, I invented a way to have cold fusion. And the patent office says, no, that's not something that we've been able to do scientifically under laboratory conditions. So I'm really betting that you don't, and I'm not issuing you a patent for this. And the same thing for these propulsion devices that violate the laws of physics. Like, well, if you claim you're violating the laws of physics and physicists haven't gone and verified this, you're probably not going to get a patent. So there's a lot of information that people don't want to give away. What they're basically saying is, I know the general gist of it is, we have this device that we built. It is an electromagnetic cavity, which is to say you build a conductor in a certain shape with nothing inside, with vacuum inside, and you electrify it, you bring it up to some high electric potential, you run electricity through it, and what they claim happens is if you run enough electricity through it and you have this device, it can spontaneously cause thrust in a specific direction. That's the claim of the experiment.
So a while back, I remember hearing about this drive, and that's a team in China had actually tested it. And do you have any information on how that test went?
The thing is, every time you perform a test, right, you have to say, what are the conditions I'm running this test under, and what are the limits of the test that I can perform? In other words, I'm going to put how much energy into this, I'm going to get how much thrust out of it, and for what I'm measuring, what are the uncertainties in my measurement? What are my measurement errors? So how much energy do I need to put in? The team in China, what they basically said is, we're going to put huge amounts of energy into this. You know, your house runs on services that measure current in amperages. You can measure power in watts. So when you have a device that you're drawing current from, that you're drawing power from, how much power do you need to put in there? Well, if you put in a certain amount of power, you would expect to get a certain amount of thrust out of it if you were using a conventional engine, right? When we talk about that conversion, we're used to, at least in America, we're used to measuring, well, I'm going to measure my thrust in something like horsepower, and I'm going to measure my power in something like watts. Well, thrust, right, horsepower, how powerful is my engine? 1 horsepower is about 746 watts. So when you talk about something like your car with 100 horsepower, that's using tens of thousands, about 70,000 watts of energy. So it's pretty energetic. And you're getting a fair bit of thrust out of it, right? Your car can accelerate pretty quickly, it can go pretty fast, and it's a pretty massive thing. It's over 1,000 kilograms for most cars. So you say, all right, that's pretty good. Now, what am I purporting to do for this device, for this M drive? Well, they're saying we put in large amounts of power. We put in kilowatts worth of power. So, okay, we're giving you this large power input. And all we're doing is we're setting up an electromagnetic cavity. We're running current through it. And what are we getting out? Well, what they said is we're getting thrust out of this. We don't think we should be getting thrust out of it because there's no engine, there's no exhaust, there's nothing like this. So you say, all right, how much thrust are you getting out of this? And the answer is tens of micronewtons. Now, newtons are not really something most of us are familiar with, but if you took something that we are more familiar with, like a kilogram under the weight of gravity, that's about 10 newtons. So that's about 2.2 pounds on a scale, or 1 kilogram on a scale. That gives you about 10 newtons worth of force. So how much force do they claim this is producing? Well, you put kilowatts of energy into it, and you're getting tens of micronewtons of thrust out of it. So that's a pretty lousy return on investment. That's a pretty lousy exchange rate. But the big thing that they say is interesting about this is we shouldn't be producing any thrust. We don't know how or why this is working because there's nothing being outputted. There's no exhaust. There's no motor turning inside. We've just run some current through this circuitry and we believe we are getting some thrust out of it. That's the claim of the people in China who tested it. And a little bit later, that's the claim of the team at NASA that tested it as well, led by Sonny White.
So these tests that NASA run were actually fairly recent, which is why this has been in the news again. So again, has NASA had the chance to break apart this machine? And I mean, they obviously know sort of what it looks like on the inside, but are there any guesses as to where this small amount of thrust might be coming from, or whether or not it's part of some kind of experimental error?
Okay, so these are some good questions. The first thing I want people to realize is we love to say NASA, like NASA is some massive, like brilliant agency that can do no wrong. And if it's verified by NASA, then it's gotta be right. I want people to remember what NASA is NASA is a very large agency that employs thousands and thousands of people, most of whom are not scientists, most of whom do not have PhDs in a scientific field, most of whom don't have rigorous scientific background and training. NASA, you can find plenty of people who work for NASA who believe that aliens are among us. You can find plenty of people who work for NASA who believe in cold fusion, as I mentioned earlier, which we know does not work experimentally. We would love it if it did, but you can find believers in that at NASA. You can even find some people at NASA who think the moon landing was a hoax.
Oh, that's great.
So you can find, when you say this was tested by NASA, what does that mean? It means it was tested by one engineer using a NASA laboratory. That's what it means that it was tested by NASA. It was tested by someone who works for NASA at a facility that NASA either owns, works at, or does business with. That's what tested by NASA means. So let's not pretend that this was like we had the whole mission control room that masterminded the Apollo moon landings working on this. No, you had a scientist. And the scientists who do this, the engineers who do this, they receive hundreds, probably thousands of these devices every year that claim to have fantastic breakthroughs. So what do? They said, well, we're going to hook this device up, we're going to put power into it, and we're going to test it, and we're going to see what type of thrust we get out of it. So they do. They take this device, they hook it up, they put a lot of power into it, and what do they get out? Well, they say that they have a device that has an inherent error to it of about 15 to 20 micronewtons, which is to say, if you hook this device up to a bowl of Jell-O and you ran the bowl of Jell-O however it's supposed to run, you might measure 15 or 20 micronewtons of thrust coming from this bowl of Jell-O. Now, does that mean the bowl of Jell-O is really providing 15 or 20 micronewtons worth of thrust? No, but it means that you're not going to be surprised to see a reading of 15 to 20 micronewtons. You would be surprised if you saw a reading of 1,000 micronewtons. Then you would say maybe Jell-O really is a propellant. Because that's the sort of thing that's way out of the realm of what you'd anticipate. Well, so what did they measure when they hooked this device up to an enormous amount of power? They claim to have seen between 55 and 70 micronewtons of thrust. And, when I look at that, I say, well, for me, when I run experiments and I say, what's my error, right? And I say, if my error is 15 to 20 micronewtons, then if I measure 25 micronewtons, that's not significant. That's not how it works. When you say 15 to 20 micronewtons is my error, what that normally means is not if I measure anything above it, then that's real. It means that's my typical error. If I see something that's plus 15 to 20 micronewtons or minus 15 to 20 micronewtons or anything in between, that's what I expect to get about, the majority of the time, about 2/3 of the time. And that's if I've got nothing. Well, the other maybe 30% of the time, I expect to get something between about double that. So not 15 to 20, but maybe 20 to 40 micronewtons, or negative 20 to negative 40 micronewtons. And then I expect to get, maybe 2.5% would be maybe another jump up like that. And so if I'm testing hundreds or thousands of these devices, when I measure that one of them does something interesting, well, what does interesting mean? For me, I would say you need to get to at least a factor of 5 to 10 above your uncertainties. You should really be measuring somewhere, around 100 to 200 micronewtons before you get interested, before you think you've really found something. Because you want to make sure the worst thing you can do in an experimental science is fool yourself into thinking you've detected an effect where all you've done is you've sort of hooked 1,000 devices up to a thing where a few in 1,000 devices are going to exhibit a positive result. And that's what NASA did in their initial tests. They had a large number of devices that they were testing. A few of them were positive results, marginally positive. And the M drive, which came in 3 incarnations, had the positive result work for 2 of them. So that was what NASA saw originally. And the reason this has been back in the news is because they finally rerun the test in a vacuum. Because one of the objections was, how do you know you're not having the air in the cavity contribute to this?
So this is the sort of error bars we're talking about here. Is the air, just, plain old air in the cavity of this device could be causing these readings.
I want you to think about that for a second. Like, when the wind blows against you, even if it's a light breeze, that's a big deal, right? If you're running a race and you've got a wind blowing you at 2 meters per second versus 0 meters a second, suddenly your world record time, if that wind is blowing at your back, isn't going to count as a world record because it's wind aided. And that's not that fast. 2 meters a second. We're really talking like 7 miles an hour there. This is not a fast speed. So if you say, well, what could be providing 15 to 20 micronewtons of thrust? The answer is, maybe you'll hear me blowing into the microphone very softly. It's going to sound like, that's 15 to 20 micronewtons easy.
So what did they find when they ran the tests in a vacuum?
When they ran the test in a vacuum, they found comparable results, which is to say, we still see this little bit of thrust that we think is slightly more than the threshold of what a null result would be. And that's what they saw. And they said, NASA validates impossible M drive. Travel to the stars must be coming soon. I would really, in a situation like this, I think this is where, you've got to decide as a human being what kind of hat you're going to wear. Are you going to wear the hat of someone who says, well, we did a test and what we saw was an effect right at the limit of what we could possibly see, and we saw something just beyond that limit, and therefore we're probably violating the laws of physics, we've probably discovered something brand new, and almost free energy and interstellar travel is right on the horizon? Or are you going to ask yourself, well, if I wanted to test this robustly, if I wanted to see a really big effect, if I wanted to verify this independently and go beyond what I would consider a possible hint of a success, what would I need to do? And for me personally, I'm really in the latter camp. I'm really someone who says, I'm not going to ask you for something that I think is unreasonable. You don't need to build me a full-scale working spaceship for me to say something's new. You just need to be significantly past this threshold of what you can see. The history of physics is littered with stories like this, with stories where people thought that they were seeing a real effect that was really just at the limit of what their equipment would detect. There was a whole fiasco in the early 20th century with something called N-rays. People thought they were detecting N-rays, right? You know about X-rays. They thought there was this new type of radiation, and so they named it N-rays. And a few teams of people had claimed to see it, but only under very specific circumstances. Like it wouldn't show up if you measured your equipment directly, but if you looked at it a little askew, you could start to see the N-rays. And there was something where if you hooked up your device in this particular fashion, you wouldn't get N-rays. But then if you hooked up your device and you put something in between the device and your measuring device, then you would see the N-rays. And so what someone did, and this was kind of brilliant, is someone went into the laboratory and just messed with some of the devices in there. They took the thing that was supposed to be generating N-rays and replaced it with a block of wood. They took something that was, supposedly hooked up and they unhooked it. And then they had the person demonstrate their lab. The person who had claimed to detect N-rays had them do the thing, and he went and showed them, and here you see the N-rays, and here you don't see the N-rays, and now I can see the N-rays. And then the person who messed with them revealed how he messed with their experiment, and it was actually a very big scandal. But what I think it really goes to is it's really an illustration of this very human problem of confirmation bias. When we want to believe in something, when we become convinced that something is true, what we tend to do is we tend to look at the pieces of evidence that support what we want to be true, and we give them extra weight. And then we look at the things that turn out to maybe be either neutral or negative information about the thing that we want to be true, and we find reasons to discount that. And that's really the thing that I worry about here, is when we say a test by NASA, can we get an independent test done? Can we get a test done by someone who hasn't gone publicly on the record at saying, I think that warp drives are real? Can we get a test done by someone who is taking data objectively? And if you're claiming this is going to make an effect of, 50 to 70 micronewtons, can we get a device that's going to be sensitive to maybe just 1 or 2 micronewtons, so that if we do see 50 to 70, that really means something? These I think are not unreasonable demands. Is can we investigate this device and demand that before we believe these results, can we make sure the results we're getting are significant and reproducible by independent teams? That's what we want, and that I think is what this would need to become actual science, instead of these stories of science right at the fringes.
It's really interesting because the stories of science at the fringes seems to be where both all the crazy stuff lives, impossible space drives and that kind of thing, but also where sometimes really fascinating stories live, right at that kind of bubble where we're just pushing up against it. Ethan, always good to have you on the show. Thanks for coming back.
Well, thank you, Rochelle.
And if you want to learn more about Ethan Siegel, his blog, or his new upcoming book, we have the links to get you started on our website at scienceforthepeople.ca. You'll also find links to our social media feeds, to subscribe to the show in iTunes, and to join the discussion by leaving a comment on our episode posts. Thanks for listening, and we'll see you next week on Science for the People.